you some background on Dan, right? So Dan Doctor is a research geologist with the U.S. Geological Survey who specializes in the study of karst, also known as krsh. So I'm from the place where we're like the type locale for it. So Dan holds a BA in geology from Colgate University and a PhD in hydrogeology from the University of Minnesota with something I didn't even know existed, which is a really amazing concept, a doctoral minor in water resources. We should think about introducing doctoral minors at Maryland. In 1998, he was awarded a Fulbright scholarship to study the hydrogeology of the classical karst in southwestern Slovenia for his doctoral dissertation. In 2002, Dan joined the USGS as the National Research Council postdoctoral associate in Menlo Park, California, where he applied natural stable isotope tracers to problems in catchment hydrology and biogeochemical cycling. His research has included the hydrology and geochemistry of karst aquifers, the assessment of sinkhole hazards, the evolution of karst landscapes, and paleoclimate records in karst regions. In other words, when your relatives call you panicking about a sinkhole in Florida, you can just give them his number. He'll love to talk to them. Dan is a fellow of the Cave Research Foundation, has served on the board of the Karst Waters Institute, and was appointed by the governor of Virginia to serve on the Virginia Cave Board for the past 15 years. Currently, he conducts geologic mapping in the Appalachian Valley and Ridge Province from West Virginia to New York. When not out hunting for outcrops, you may find him at home entertaining his wife and 2 cats with his vain attempts to learn to play the guitar. Before you start, I have one question for you. Is there a YouTube channel? No, with you playing. No. Okay. Well, without wasting more of your time, let's welcome Dan one. Okay.
Thank you. Thank you, Ved. Thank you. No YouTube channel yet. I share music with people sporadically, but if you send me a note, I might just share something with you. Yeah, perfect. Yeah. Karst, Ved correctly pronounced in Croatian, krš. In Slovene, the word is kras, and I'll get to that. We call it karst. How many of you have heard this term before? Okay, this is a room of geoscientists, so okay, it's not surprising. I can tell you though, my mom didn't know the word karst before I got into, actually going to do it for my PhD. I didn't even know what the word was until late in my undergraduate career, but we'll get there. So what is it? What is it? Well, karst is a landscape. It's a landscape that's characterized by the features that are found on the landscape and the features that are found in the subsurface, natural voids in the subsurface resulting from the dissolution of the bedrock. And the bedrock has to be soluble, and in general, the most soluble rocks are carbonates and evaporites. Limestones, carbonates, and salts, evaporites, things like halite or anhydrite and gypsum. And the features that you get on the landscapes are really characteristic. Sinkholes, but caves, underground streams and sinking streams, springs, and the list of terminology goes on and on. I won't bore you with it. But here's a photograph of the Greenbrier Valley of West Virginia that I took at the Appalachian Karst Symposium just last month. And on the field trip that I partially led, we went to this site. We could see a row of sinkholes and housing developments going up all around. And just around the bend from the road that you see in the background was the entrance to this tourist cave, Lost World Caverns. Now, if you were, like most people, just a home buyer and not really knowing that there was a cave and potentially in your sinkhole, you wouldn't really understand that the scale of voids that are in the subsurface is of this magnitude. And let me start the pointer. There we go. There's a set of stairs for scale. This is quite an enormous room, and it's worth seeing, Lost World Caverns. And it's not unusual. if you're on the cave tour and you get to one part, there's a little wooden podium and you can look up above you. There's a sign that says, look up. 12 stories above, you'll see the sunlight shining in through the natural entrance. It was discovered in 1942. A young man was the first to reach the bottom by rappelling down 120 feet till he landed on the floor of that large chasm. And this is me looking up, taking a photo of rays of sunlight coming in from a hole on the surface through a sinkhole down into this enormous chasm. Looks like this. And, you know, we see these things when we take tours of them and we think of them as sort of anomalous, right? There's a cave. Oh, great. You know, you drive down I-81, you see a sign for Endless Caverns. You'll see a sign for Shenandoah Caverns. You'll see a sign for Melrose and Luray and Grand. And you go and you tour these caves. You say, wow, what a great little trip I took. It was a nice little anomaly. But everything in between, generally, we don't think of as having this. But it's there. And we only are able to explore and really understand and appreciate just a small fraction of what's there. The reason I titled the talk the way I did, and I'll get there, is it's about perception and reality. Like, so what do we perceive as we drive down the highway? Are we thinking that there are large voids in the subsurface? Probably not, because we don't see them. And I've been a karst scientist now for good 25 years, and I'm just constantly surprised at what people don't quite understand about the subterranean surface, even geoscientists, even professional hydrogeologists. I was on a field trip here in Southern Virginia, and one of my colleagues, as we're entering this cave, now this is a concrete pad for a railroad that goes through the cave, and you know, we were walking through the cave from one end to the other, and he turns to me and asks, is this natural? And, you know, because there's a railroad moving through it, you could say, well, I can understand why somebody wouldn't think it's natural, except it's called Natural Tunnel State Park. This is the other side of that cave. You don't ever get out of sunlight. But you do get to near darkness, total darkness, and then you come back out and you see the other end of the railroad track. It's a natural tunnel that was utilized for the railroad. It's pretty far southwestern Virginia, so it's kind of hard to get to. It's not anywhere near any big metropolitan area, but it's a wonderful place. I highly recommend going to see it. A little closer to us is the Natural Bridge. How many of you have been to Natural Bridge? Okay, maybe a third of the room. Now this one, you know, you might, no, there's no railroad, there's no road. There is a road on top of the bridge. Do you know what road it is? Route 11, yep. Goes all the way down the spine of the Shenandoah Valley and crosses the Natural Bridge here. But this was known about since the time Thomas Jefferson wrote about it in his notes on the state of Virginia, saying it's the most sublime of nature's work, so beautiful and arch, so elevated, so light, springing as it were up to the heaven. The rapture of the spectator is really indescribable. And that's kind of how I felt when I first went into caves, like, wow, this is pretty incredible. But again, my perception of it was, wow, this is just a crazy anomaly. Gosh, isn't that cool? Go from one place to the next. But then as I became a scientist, I began to realize that this is not an anomaly. This one might be in the terms of its scale, but the fact that these voids exist and they're in the subsurface is not anomalous at all. Okay, so the title of my talk, The Allegory of the Cave. Now, Plato in the Republic wrote about a short passage in which he was talking about human beings and their perception of reality versus truth. And for him, the truth was a higher truth, understanding the forms, the higher forms. But in the allegory, he describes prisoners. And now here's the poor man who's the prisoner. And he's chained to a rock and he can't turn his head. He's forced to look at the wall of the cave. But behind him are the masters. And the masters are throwing shadows against the wall of the cave of small figurines that they're just like puppets dancing about. And they're showing these shadows to this poor prisoner. And all he knows of his reality are these shadows, until one day one of them is freed and allowed to go up into the light and sees for the first time the sun and the reality of the world outside. And this fellow here is the person who's now enlightened by coming out of the darkness and into the light of day. And these are the poor souls still stuck in seeing just the shadows on the wall, not really understanding what's real from what they're being shown. In Plato's Allegory, to gain enlightenment about the true nature of the world, you must go out of the cave. In Karst, in order to gain enlightenment about the true nature of the subterranean world, you have to go into the cave. Now, some of you may have seen this. You know, early cave explorers, they were also fascinated by what they saw. This is a artist rendering from the famous book, Jules Verne's Journey to the Center of the Earth. And you might look at this and think, wow, what a fantastical concept for a book that clearly is fiction and sort of fantastical fiction. And surely something like this could not exist on Earth until we find it. How many of you have seen this cave? A handful. No. This is a cave in Nica, Mexico, that was intercepted during mining. It's only 120 meters deep, so it's not the center of the Earth, of course, but it is pretty remarkable and not too dissimilar from the woodcut drawing here. Next to it and deeper in the same mountain area is another cave, the Cave of the Crystals, at 290 meters depth. It's 136 degrees Fahrenheit. It's like an oven. It's almost 100% humidity. That's why the man wears a respirator. There's an airlock to get in there. Back when they were exploring these caves. Now they're totally flooded. They've stopped the mining and they've reflooded the caves. But this made the cover of Geology in 2007, and it was quite a revelatory paper for me too. I mean, even as a karst scientist, like, whoa, look at that. That's crazy. I won't go into the details about how the crystals form, just letting you know that they're selenite, it's gypsum, and it formed in a pocket of a void full of water that transformed the anhydrate that was deposited during the hydrothermal ore deposition, transformed the anhydrate to gypsum over time. But the walls surrounding where these crystals are is carbonate rock. So initially it was all dissolution of the void space and then later filled in with the crystals. And you can see in order to expose the caves, they had to pump down the phreatic level of the water table down below, down to 760 meters. It was an awful lot of pumping in order to facilitate the mining. But the point is that these caves, they form by the process of dissolution of the rock by groundwater. How do they know it's groundwater? Now, the hydrothermal minerals in there have fluid inclusions that record hypersaline brines, which is not unusual. But the fluid inclusions in the gypsum crystals, the selenite, show meteoric water, groundwater that replaced the brines over long periods of time. So it's groundwater. It's the stuff that we mine and drink ourselves by putting down wells. So what is groundwater and how does it actually move to create voids like this? A couple of years ago, the USGS updated and unveiled a brand new diagram of the water cycle. I don't know how many of you have seen this. They took in input from several people. I did not comment, otherwise I would have made some comments, but it's out there. And there's groundwater recharge over here. One comment I would have made is, okay, they're showing a more or less porous medium here as how we think of groundwater moving in the subsurface through the pore space, the tiny little voids, interstices between the clasts of sand or clay or even sandstone. There's pores in rocks. But how do you get all that water to just pop up at a spring? That's the question. That's the question that would be nice to answer in a diagram like this, because we all have experienced springs, and they're a characteristic of karst, not just karst, they're all over the place. How does groundwater move? This is Henry Darcy. I think it's arguably fair to say he's the father of hydrogeology. Darcy was working in France. Darcy understood karst because the water that he was using in his experiments came out of a cave, out of a cave spring. But his problem was how to filter the water to make it clean for a hospital that he was charged with supplying water for. And so he devised the permeameter, um, basically a simple device through which he could filter water by filling a column full of sand, pumping water in at the top and measuring the head there. And then as it flowed out the bottom, measure the head there. And the difference in the head would be the gradient through the material, which would be sand. And you can determine the resistance to flow by the material in the column. And according to a simple equation, we now know is Darcy's law. Got the S, Darcy's law. So Q is the flow rate, A is the cross-sectional area of the column, DHDL is the change in the head across the length of the column or the hydraulic gradient, and K is that conductivity of the material. K is the parameter that encompasses an awful lot of things. How the water actually moves through the material. And this simple equation is the foundation of all groundwater models. I'm sure most of you have ever had hydrogeology, have learned it. Some of you may have even taken it and implemented it into a water model. The issue that you need to understand with Darcy's law is that it's applicable in a very narrow range of conditions. And these, of course, are outlined almost always in the textbook and always highlighted by the professors who teach hydrogeology. But how often do we find these in nature? A homogeneous, fully saturated porous medium with no turbulent flow, no change in head potential. In other words, it's a steady state, so you don't have variability in the head across the domain of the area that you're interested in, and all the boundary conditions are known. Then you can apply Darcy's law. And if you have a model like this that we actually use in hydrogeology labs, and you inject a little bit of dye down a artificial well and fill this with clean sand, yes, you will get plumes that will behave according to Darcy's law. But all these conditions apply pretty nicely in something like this. What happens when we go to nature? It gets a little bit more complicated, doesn't it? We have different rock types that are layered into probably a channel of a stream, let's say. We just want to know what the contaminant could be moving through a natural deposit of sand and shale and clay. Well, in order to apply Darcy's law, you have to really simplify. You have to find the hydraulic conductivity or estimate it or look up in a table what it is of each of these different layers. And discretize your model, simplify it down, get rid of all the heterogeneity, apply the known boundary conditions, and when you're all said and done, you get some kind of a three-dimensional discretization of what is really a very heterogeneous system. And you apply it. And now, these models, and you calibrate them to the head levels in the data, which are usually wells, in order to get the model to run. And in the end, you can pretty accurately estimate the movement of groundwater and the quantity of groundwater that's moving through the system, but you can't do transport of contaminants. That's the rub, is it really fails when you try to estimate the transport of solutes in the water. How do we know this? This is an experimental site in Columbus, Mississippi. It's in the coastal plain, so it's pretty much just a sand aquifer. And they permeated it with monitoring wells, and they added tracers to these wells. And then over decades, they've been monitoring how the movement of these solutes in this mostly sand and gravel aquifer move through the subsystem. And the overarching conclusion is that preferential flow paths, things that are on the scale of a decimeter and smaller, control the flow. They control the flux. And that's kind of remarkable, because if you have a decimeter scale preferential flow path, you more than likely have turbulent flow or something approaching a velocity that would invalidate Darcy's law. Darcy's law becomes invalid at Reynolds numbers greater than 1. Turbulent flow begins at 2000, but greater than 1. 1 is a very small number. That's flow of like 3 millimeters a second of groundwater. That's fast. Above that, you can't apply Darcy's law. And yet we do it all the time. But I knew from a young age, as an aspiring naturalist, a Webelow Scout, here I am, age 11, before I go to my very first overnight camping trip. I knew from a young age that water came up out of the ground. Why did I know this? Well, because I grew up in Pompton Plains, New Jersey. It's a big glacial outwash plains, flat as can be. And my school, my elementary school, was over here. And then over here was a big area of undeveloped woods, wooded flat, but marshy, kind of marshy area. And this stream that you see in blue running through here is a ditch that was dug to help drain this area and help prepare it for eventual development. There was a church here that my family would go to. And so I would ride my bike after school or whatever I had time. I would ride my bike and drop it by the side of the road and walk into the woods. And I was very curious about, now this development wasn't there at that time. This is an aerial image, so you can see it's still fairly wooded. This is from very recent, but now we have LiDAR. Well, LiDAR is a very high resolution topography taken by a laser on a plane. And this is an image of the LiDAR for that same area. And I used to walk through these woods and I'd find little channels like this one here and this one here and this one here. And I'd see water in them and be like, where's that water coming from? I'm really interested. So I just follow it all the way up. I just follow the stream up to where in there, what did I find? Spring. Just like that. Water's just coming right up out of the ground. It's not a seepage face, even though it's mostly unconsolidated sand, gravel, and boulders and things. It's a discrete zone, a little conduit that's flowing out. And I can tell you that that's not laminar flow. That is definitely turbulent flow, preferential groundwater flow. You can't really, I didn't have a video, but you can see how much water is pouring out of this spring. Just little springs, but they're pretty pervasive. Now me, as a kid, I kind of idolized Columbo. I always thought of myself as kind of a detective. So much so that, I dressed up as him in Halloween one year. And I thought, I'm going to figure out why springs exist. That was what I wanted to do. So I was going into college and like, gosh, I really want to know why springs exist. So I go to college and, take all the classes I can that have anything to do with water resources. And this was the classic textbook. How many of you have used this textbook or had it in class? Okay, 5, 6 people, yeah. Classic Fetter, really wonderfully done textbook. And the cover shows a lot about what you learn. You'll learn about Darcy's Law. You'll learn about how to draw a flow net. You'll learn about, how to calibrate wells and confinement and unconfined aquifers. You'll see how to construct a flow net like this. This is classic Tothian theory of groundwater flow. These are lines of equipotential and flow lines that cross lines of equipotential. Does this explain how a spring forms? Not to my mind, it didn't. Like, where is the spring? Is it going to be here? Is it going to be here? Is it going to be here? Is it going to be everywhere? Everywhere that these things, because these are just a few of the flow lines, right, that would cross. In theory, the whole thing is moving water out. So does that mean the whole landscape is just coming up like a lake? Well, we see lakes, but we see springs. So back to the cave. What are we learning from Darcy's Law? What are we learning from the professors who are showing us the theory of groundwater flow? So here I am wanting to learn more about something that's what I had in my head already, which was a discrete point on the surface where water's coming out. And so I go back to the into the index and I look for springs. Oh, wow, there's all of 2 pages on springs, but there's diagrams, which are really cool. Really nice diagrams. And boy, one did catch my attention, the sinkhole springs. This one over here, that's really super interesting. What is that all about? And so I go into the index a little further and I find, oh, there's karst. Okay, well, there's actually 10 pages on karst out of this 615-page textbook. What is karst? But that's all. The professor didn't really explain it. I didn't really have any other grounding in it. And yet I knew that that's where all the big springs were because, you do a little research on your own. You find out, yeah, big springs in karst. So I go to graduate school and I wrote a letter to my advisor. I said, I want to study karst. And he was a karst. Calvin Alexander at University of Minnesota was someone who specialized in karst, but never got students who wanted to study karst. And he was about to go on sabbatical that year. But since my letter said I wanted to study karst and get a PhD, he was so excited. He said, I'll take you, even though I won't be there first year. So come and you can study, just take classes, and we'll start research the next year. And it just so happened that that second year, there was a field studies on karst at Mammoth Cave. Now, unlike a lot of people who study karst, I was not a caver. I didn't grow up like with this as a hobby of mine. And so this was one of my very first wild caving expeditions in Mammoth Cave. It was like an 11-hour trip. It was awesome, but you can tell how green I am. I'm wearing white socks. Really not a smart thing to do if you want to wear them again. But over time, I ended up doing more and more caving and getting myself enlightened as I went down deeper into these tunnels. I was in Minnesota. This is sort of the landscape of the karst of Minnesota. It's in the driftless zone where you had prior glaciation, but not a lot of till that was left behind. And so you see this bare bedrock of limestone covered with loess. But the caves aren't particularly spectacular. That's probably about as good as it gets. Some holes like that in this quarry wall. Sinkholes, though, do abound, and they're the collapse of the overlying sediment on top of the bedrock. And I learned an awful lot. This diagram I'm showing here is an excellent rendering of what a typical Midwestern karst terrain looks like. One of the misconceptions people have, and back to perception and reality, one of the misconceptions I think people have about sinkholes is that they're caves that have collapsed. Now, some of them are, but most often they're just little voids in the regolith or the soil cover on top of the karst, on top of the limestone, the carbonate bedrock. The bedrock dissolves right at that interface between the overlying sediment and what we call creates an epikarst, or a very uneven surface. And often you have water moving through the soils and through the process of suffosion, creating voids. And if those voids collapse suddenly, that's what we call a cover collapse sinkhole. And those are the things that are really the hazards to property and infrastructure. So sediment on top of bedrock is really key for understanding hazards in karst. But also what we do to the landscape is super key. So putting trash down into a closed depression is really just a direct conduit into the groundwater system. And all these bedding plane fractures, or for example, putting a septic tank on top of the epikarst, and if that happens to leak, it goes directly down into the underground aquifer. And flow can go very quickly, almost unfiltered, like a pipe in your house, down through a fracture, along a bedding plane parting, and come out through a cave, a stream in a cave, and into a spring. Or if it's intersected by a homeowner's well, can go right up into their sink. And that's no joke. I'll get back to that. But as a graduate student, Minnesota was just not all that exciting, and it was super cold. So I had a little wanderlust. So I thought, well, where can I go to really get a grounding in karst? There are lots of places around the world, right? Some of you probably have seen photos of the wonderful tower karsts in China. And this is the Li River here. Maybe Vietnam. This is Hang Son Doong, currently the largest cave passage in the world, largest known cave. Perhaps the Tsingy karst in Madagascar, these knife blades of limestone sticking up out of the forest. But no, I thought I should go to the classical karst of Ved's homeland, former Yugoslavia, the Dinaric karst. And actually, like I mentioned, the word karst comes from Slovenia. Now, the one place I couldn't go was Pandora, even though Pandora did take some of its inspiration from karst of China, as you can see. Wasn't able to go there yet. The word karst originated in Slovenia. So we're going to take a real quick trip to southwestern Slovenia here on the border of the Adriatic Sea. And as Ved mentioned, I ended up going there to do my doctoral research on this particular system, which is the classical karst, or the Kras region. So in Slovenia, this name Kras is the name of the region. It was written about in the 1600s by a guy named Janez Valkard Valvasor. And Valvasor wrote a geographical treatise on this part of the world, and he wrote in the German language, and that is why the word karst was translated into German. The word Kras was translated into German and became karst. And that's currently what we have as the word we use internationally today. What does it look like out on the surface? Pretty spectacular. This is the town of Scotian. It sits atop a natural bridge in limestone. There's a river passage here, a cave passage that flows across and through this large collapsed sink or doline. The river crosses another natural bridge and goes through another doline and eventually sinks down outside the view at the bottom of the picture here into a large cave system called the Skocianskie Yama or Skogin Caves. This is looking back to where the river was sinking here, and there's a little caver for scale. This is an enormous river underground with an enormous cave that is amazing. It's a World Heritage Site. I highly recommend visiting. There's a bridge that crosses the river 300 feet above in the middle of the cave passage, nowhere near the roof. It's just quite amazing. What happens hydrologically in this system? Well, this river sinks right here at the entrance to the Skogin Caves and flows 40 kilometers through the limestone massif out to some springs on the coast of the Adriatic Sea here called the Timavo Springs. A river underground 40 kilometers. And we know this because you can intercept it along its path by other vertical shaft caves that go down more than 300 meters to intercept the river. And these have been instrumented and they've dye traced it. They dye traced it in the early 1900s, but they've instrumented it to follow the flood pulses as they go through the river system and come out the springs. Here's a view. Oh, sorry, let me jump back. So we're going to be looking from the springs now back towards this way, towards the city of Trieste, Italy. Here are the springs. They used to be part of the water supply of Trieste, Italy, until there was an unfortunate chemical spill upstream on that river sinking at the Skogin Caves. And then that was taken offline and some other nearby springs were used as water supply. But this was a system that I was studying for my PhD. I'm not going to go into that. That's a whole nother talk. But needless to say, I did not create a groundwater model. The Skogin Caves are here. There's another amazing cave system right in between called Grotto Gigante. How many of you ever heard of Grotto Gigante? No one. Well, I'm surprised because you are all geoscientists and there happens to be, well, first of all, let's get into the scale of this cave. You can see that the height of the total cave passages is 252 meters, but the big room that you can tour is more than 100 meters tall. There's the Washington Monument for scale comparison. Quite an enormous chasm. It is so large, there's a geodetic experiment in the cave, a pair of horizontal pendulum that can measure seismic activity and can measure earth tides. It's run by the University at Trieste. They can even measure the vibrations that occur when that river that flows through the karst floods, because it's such an amazing seismic event. The other classic thing you see in classical karst are sinkholes. And this is something that, of course, we associate with karst universally, the presence of sinkholes. But just because you don't see sinkholes on the surface does not mean there is no karst in the subsurface. And that's a key point. So approximately 15% of the world's land area is carbonate rocks, soluble rocks. What about the US? When I joined the USGS and I got this present job that I have, one of the first tasks I was assigned was to help make a map of karst of the US. And my colleague Dave Weary and I did this. And it's surprisingly that's not too different from what that worldwide. It's about 18% if you add up the soluble rocks, carbonates and evaporites. These other areas we call pseudokarst. These are places that host caves and sinkholes that are not in soluble bedrock, but are things like lava tubes in young basalt flows, where you do have traversable caves and you do have lots of large collapse. And hydrologically, it functions like a karst, but it's not the true karst that we think of having formed by the process of solution. So pseudokarst includes sedimentary piping features, and thermal karst out in Alaska and other areas with permafrost. So all in all, there's a lot of karst in the US, but it just doesn't get a lot of attention. We put the map together. It's a GIS database. You can download it. It's a bit complicated, so I'll walk you through a little bit. This red line through the top here is just the limit of the last glaciation. So the carbonate rocks up here would be covered with some glacial deposits. Out here, you have less than 30 inches of precipitation annually, and over here it's more than 30 inches of precipitation annually. And so we basically divided up our legend of rocks by whether they're covered karst or covered carbonate or evaporite rocks, what the climate is, and how well indurated they may be. Because some of them on the coastal plain are just loosely consolidated sediments. In fact, a lot of Florida, if you go and look at the Ocala limestone, for example, you can crush it with your hand. It's so loosely consolidated. And there are lots of superlative places in the United States that I can talk about. So Mammoth Cave here, still the longest cave in the world, 500 miles, almost 420, I believe, 420 miles. Tears of the Turtle Cave in the mountains of Montana is currently the deepest cave in the U.S. Carlsbad Caverns used to hold that honor, but it's still one of the largest rooms in the world, the big room. Of course, Florida is known for many sinkholes, and then we have Minnesota. I'll throw in Mystery Cave. It's a beautiful cave in Minnesota. But one of the, I wouldn't say criticisms, but one of the questions I would get from the map is, yeah, there's all these great polygons of karst areas, but what's the degree of karst development in any one area? And so we weren't able to do it at that time, but then as more and more modern computing techniques became available, we were able to extract closed depressions from the land surface. Now here's an aerial photograph or satellite photograph near Horse Cave, Kentucky, in probably the densest area of closed depressions in karst in the United States. And you look at an aerial photograph like this and you'll say, yeah, you'll see lots of little closed depressions, you know, arbors of trees and such. When you throw on LiDAR, shows you what's really there. Again, what's our perception and what's our reality? A little bit different. And so I took it upon myself and others who helped me. We made a computer program to extract these closed depressions from digital elevation models for the whole country. And we were able to make a map like this, which shows sinkhole hotspots overlain on the carbonate geology of the US. So now we can see where the real high degree of karst formation occurs. And those who work in karst will recognize these areas are also areas where there are an awful lot of big caves. You know, Eastern Tennessee and Central Cumberland Plateau region and Central Kentucky where Mammoth Cave is. But then here and there, Missouri is known as the cave state. There are just lots and lots of caves in these areas, but there are caves all throughout. You just don't see the expression of the karst at the surface. You see the carbonate rock instead. And so my esteemed colleagues in the USGS would say, well, that's fine. It's carbonate rock, but don't call it karst. Because it's not, because karst is the topography. Well, for the remainder of the talk, I'm going to hopefully convince you that that's a fallacy, and we really need to focus on not just the surface expression of the karst, but the rocks themselves. Because Darcy's really not done us any favor. I will go as far as to say Darcy's law is a red herring when it comes to understanding hydrogeology, because preferential flow dominates. And it doesn't matter if it's limestone or sand and gravel, as I showed you for the coastal plain. Preferential flow dominates flows in the subsurface, and they're integrated in a self-organized network, just like caves are the expressions of the trunks drainages of self-organized networks. Now, I work for the USGS. I should have prefaced this talk by saying everything I say tonight is my own opinion and not an opinion of the agency, nor that of the federal government. And I would just show this website, which is I pulled down from the other day. What is groundwater and how does groundwater move? Well, contrary to popular belief, groundwater does not form underground rivers. I guess that negates the classical karst. It fills the pores and fractures in underground materials, such as sand and gravel and other rock, much in the way that water fills a sponge. And of course, that's correct. That's correct in terms of the filling, but the movement is through flow paths that are self-organized. It moves slowly, typically at rates of 7 to 60 centimeters or a few inches per day. Well, we know from dye tracing that just doesn't hold true. even in some of those sand and gravel aquifers that I was showing you. My esteemed colleague, Stephen Worthington, and my PhD advisor, Calvin Alexander, and others, wrote a paper a few years ago on definitions. What's a definition of a karst aquifer? Okay, if you're not going to say the whole, wherever you have carbonate rock, it's a karst, then how are you going to define what is and what isn't karst? If you take it that a well has to intercept a cave in order to be in a karst area, well, only less than 1% of all that carbonate rock is going to be karst. How about wells that intercept a solutional channel that has turbulent flow? And to be turbulent, you have to, it only takes a centimeter width of a fracture to generate turbulent flow. So if you get wells that intersect that space in an aquifer, then you get about 5% of the total carbonate rock. Well, that's really not adequate either. How about aquifers that underlie what we call karst landscapes, or those areas that have, let's say, those sinkhole hotspots that I showed? Yeah, you might say, okay, 50% or so. But if you start to use the real hydraulic criteria that define turbulent flow, fast-moving groundwater flow, self-organized, integrated groundwater flow, you start to understand that much, much more of what we consider soluble rock really does fall into the definition of a karst aquifer. And just to illustrate a couple of examples is what's the consequences if you don't ascribe to that view? A few years ago, some of my USGS colleagues were working on, in Florida, an assessment of the vulnerability of the Miami-Dade water supply to contaminants. There was some quarrying going on in these lakes here, and the well field for the city of Miami-Dade is here, or the county, I should say, and the city of Miami. So these little black dots you see are all pumping wells that are used for water supply or monitoring. And in red, surrounding them are the zones of protection, or this is the outer protection zone, and the estimated time of travel it would take from this zone to go to one of these wells. So here, this time of travel is estimated to be 210 days, here 100 days, here 30 days. And you can see within a kilometer of distance, they're saying, oh, it'll take 30 days for that water to travel to a well. And then they did a dye trace. They wanted to see, okay, let's test this. Let's get some real hard data to test our model. And they put in about 50 pounds of rhodamine WT water tracer, which is a beautiful, bright, pink colored fluorescent dye, into a well. And they wanted to see it travel 100 meters to another pumping well and get the hydraulic parameters in between. And what happened? They turned the city's water supply red. Red dye streaming through the faucets and shower heads in northern Miami-Dade. Underwear was turned pink in the washing machine. It's Florida. Why not? Involved a complicated test by the Water Management District, the Department of Environmental Resources Management, and the USGS to find out how quickly the water moves through the limestone near the well field. And the preliminary results provoked nothing less than shock in the scientists who performed it. Why? Because they were assuming it was a homogeneous, porous medium without any preferential flow. And this is all published, so you can go online, you can look. But what they thought would take 30 days went 100 meters in a lot less time. Sorry, a kilometer would have taken 30 days. Instead, a third of a kilometer took 1 day. Much faster. And so what's the lesson here? Well, using a single porosity equivalent continuum porous media model probably didn't do the trick as well. And effective porosity, that is the open space within the aquifer that actually transmits the water. It's one of the parameters that's used to define these time of travel zones in a groundwater model. And there's great uncertainty as to the complexities of these high velocity preferential flow conditions and whether or not those have been correctly approximated. This can actually have human health considerations. Okay, this was a water supply for Miami. Fortunately, no one was sickened. This wasn't a contaminant that went in the aquifer. It was a non-toxic dye tracer that we use typically in karst terrains. But what happens when it's a contaminant? And this is what happened in Walkerton, Ontario. Ontario is a thick, underlain by, this part of Ontario is underlain by thick Silurian carbonates and dolomites. Not known to be known for caves or anything like that. But it was the largest water quality disaster in Canadian history. 2,300 people became ill and 7 people died because of E. coli contamination from agricultural runoff, from manure from farm fields that just was flowing over the surface in the ag fields during a heavy flooding event. And there were other factors that contributed to this disaster. For example, the water managers were not properly chlorinating the well water. They were not maintaining its quality. But the models showed around the pumping wells these zones of influence and travel times that were, again, not dissimilar to what I showed in Florida. Hundreds of days to go, a few kilometers, when in fact, so for example, a 30-day time of travel zone was about 180 meters from one of these pumping wells. But when they do the dye traces, they found the travel time was more like 3 days. And the velocities are an order of magnitude that were predicted. And why? Because when you go down the well, you'll find the individual bedding plane partings controlling 50% or more of the flow. And they're not always the same bedding plane. These wells were correlated, but it was one well had a bedding plane controlling most of the flow up here. Another well had a bedding plane controlling most of the flow down here. These were spaces that were a few centimeters at most in width, but they were controlling the flow and contributing to the contaminant transport. No big caves, no big sinkholes on the land surface, and yet there is solution in the aquifer, and it really ought to be treated as a karst system. I see this all the time when I'm out in the field mapping. I see rain flowing, runoff off of ag fields that flows through a farmer's field and goes down into a sinkhole directly into the subsurface. There's no natural filtration. I've even conducted dye traces into rock outcrops that have little voids like this. This was Nathan Farrar. He was an intern with me back in 2010. We conducted a dye trace to see what the contributing area was to a spring locally. This was adjacent to a farmer's field. There was pasture land. The fence is not easy to see, but there were cows that could have walked all over this place. And the next day, after we put this fluorescent dye into the ground, this is down into that little hole. You could see they couldn't even see the bottom of it, and the water went down. The next day, I got a call from a lady who said she has green water coming out of her faucet. It had gone 100 meters laterally and about 30 meters down or 100 feet down to her well. Now, how did I get this phone call? Well, I had gone out. I knew how to do a dye trace. I know you tell the local authorities, you tell the local people. I put out flyers in the local communities to say, if you see green water, give me a call. And they did. The next morning, I drove out there. And I had to tell her, I'm sorry, your well turned green, but now you know that the water going down a sinkhole in that farm field next to your house is coming out of your well. Fortunately, she had a charcoal filter and she had a UV filter, so she was taking precautionary measures. The interesting thing was hers was the only well in this little cul-de-sac of about 10 houses that got the dye. None of them else did. And all the other homeowner wells were completed at about the same elevation in the aquifer. It just happened to be this one. So what's the perception? Again, if all you are is learning in class Darcy's law, learning about porous media modeling, porous media flow, and you take that and you try to apply it to any problem that comes your way, you're no better off than the prisoner in the cave. Your reality is skewed by what you see in a textbook, not what you see in the field. And so I hope what I've demonstrated is that we need to not consider just these hotspots where we see karst topography as being areas where we need to consider how to apply hydrogeologic concepts in karst areas. We need to broaden that perspective. Hopefully, you'll become enlightened like the man who went down into the cave, not the man who came out of the cave. And I invite you to come into a cave with me sometime. Thank you very much. And as is the custom, there are no questions, but we will take a short break.